Welcome to our second lecture of this semester. Today we're talking about functions and graphs. So here are all the topics we'll cover today. Again, I leave this slide in here so that you know what is covered during each lecture, and it's an easy way for you to check back about what we're going to talk about. All right, so the main topic for today is to talk about a function. A function is a correspondence between two different sets. The first set is called the domain, and the second set is called the range. And we need each member of the domain to correspond to exactly one member of the range. And it's important to note that not every correspondence between two sets is a function. And we're going to see an example of that next. So when we look here, we're going to determine if each of the two correspondences is a function. Let's look at A first. And we look at our domain, which is on this side, and our range on this side. And we think, does each domain have exactly one range? And it does, because each of these have exactly one arrow leaving from the input side. So the domain side or input side has one arrow pointing to each of the output sides. I don't care that 9 has two arrows pointing towards it. I care that only -6 and 6, -3 and 3, and 0 each have one arrow leaving it. Now this is a function. Now let's look at side B. When you look, you see that George Bush has one arrow, which is great, but Bill Clinton, the other George Bush, and Barack Obama each have two arrows leaving their side. So this guy is not a function. All right. So basically what you're looking for is two arrows leaving the left-hand side or one for each of the items there. Now, we call something a correspondence a relation between the first set, our domain, and the second set called our range, if each member of the domain corresponds to at least one member of the range. So a non-example is easier to see here. -6 goes nowhere in this correspondence, therefore it is not a relation. Now, we focus a lot more on functions than we do relations, but it gives you a little context when you see that word come up. So now we're going to determine if this relation is actually a function, and we want to identify the domain and range. So anytime you're given a bunch of ordered pairs like this, remember that this is our x and this is our y, and so our inputs are typically the x side and the outputs are our y side, okay? So each of my inputs are 9, 9, and 2, and each of my outputs are -5, 5, and 4. And so when we want to actually look at, okay, is this a function? It's often helpful to draw out these kinds of diagrams, because very clearly we can see that 9 is being mapped to two different values. So this is not a function. But we can still tell what its domains are. The domains are the numbers on the left-hand side here, 9 and 2. Hello, 2. And on the right-hand side, we have -5, 5, and 4. And so that's our range. Now we're going to think about, is this relation a function? We're also going to identify the domain and range. And looking at the lovely little mapping here, you can clearly tell this is a function because each input has exactly one output. And we can note that this side is our domain and this side is our range. And we would just list those values next to our domain and range. Alrighty, third one here. We need to again tell, is this a function, and identify the domain and range. And it's very tempting to say it's not a function because there's only one thing in our range on this side. But what we care about is that everything on our domain side has exactly one arrow leaving it. And that is true here. So this is a function. Our domain is -5, 0, and 6, and our range is just 3. And that can happen, but that's totally okay. Now, for functions, we typically use a particular notation for functions. And you always want to think the inputs, so our members of the domains, are our values of x whenever we get them, and that's what we substitute into the equation. And our outputs are the members of the range, are the resulting values in y. So we use this notation, which is read as f of x, or f at x, or the value of f at x. So essentially, f is going to represent all those different operations we do to x. So I could write something like f of x equals 3x plus 5. So essentially, f is going to take x, we're going to multiply it by 3, and then we're going to add 5. And that's what f represents, essentially. Now, every time we're given a function, so we say f of x equals 2x squared minus x plus 3, we want to find each of the following. So f of 0. Every time you see whatever's put in parentheses, where we typically write of x, that is exactly what you're going to plug in for x. So I'm going to end up with 2 times 0 squared minus 0 plus 3, which is just 3. 0 plus 0 plus 3. Now we do the same thing with f of -7. 2 times -7 squared minus -7 plus 3. And this is a really good example of why parentheses are really useful. You got to make sure that the negative gets squared along with the 7. So this becomes 2 times 49 minus negative, I'm just going to go ahead and switch that to a positive, minus -7 plus 3, which is 2 times 49. I don't think I can do that in my head. I'm whipping out my calculator real quick. 2 times 49 is 98, plus 7 plus 3, 98 plus 7. Well, that is 105 plus 3, and now we have 108. All right, so f of -7 is 108. And we'll keep going. We can plug in things that are also variables. So I could plug in 5 times a in place of x. And you know what? It does the same exact thing. I'm going to say 2 times 5a squared. So notice 5a goes exactly where the x goes, minus parentheses 5a plus 3. And we'll just simplify this a little bit, but of course we're going to have a's in here. So I'm going to have 2 times, when I have a square like this, it goes to both values. So I have 25a squared minus 5a plus 3. And I'll simplify that one more step to have 50a squared minus 5a plus 3. And that is it. That is what f of 5a gives us. And just note, I plugged in 5a everywhere I see an x. So whatever goes in parentheses goes where the x is. All right, we'll see that one more time. We're going to have here 2 times, all right, a plus 4 goes in place of the x squared, minus a plus 4 plus 3. Okay, well, here's a quick reminder. We got to FOIL this guy out. We're going to jump to the top to do that. A plus 4 squared. Now, the way I distributed the square in part C cannot be done here in part D. I can't just distribute the 2, as nice as that would be, because it actually, we're stuck with this addition sign in the middle. So this guy, instead, we got to FOIL it all the way out, which, if you remember, is doing first, outer, inner, last. So we're going to multiply the first, which is a squared, a times a. And now we're going to do the outside, so that's a times 4. Now we have 4 times a, and then the last, so 16. So we've multiplied all the different components in here, and that's what we get for that first bit. And so I'm going to write that down now, a squared. I'm going to go ahead and add 4a and a times 4 to get 8a plus 16. And then can I, no, that's okay. We're just going to squeeze it in here, I think, minus a plus 4 plus 3. Okay, so moving on to the next line, we'll keep going. This 2 now needs to be handled. Notice it was 2 times the a plus 4 squared, and I FOILed out the a plus 4 squared, and now I'm going to distribute 2 to each term. And that's the proper way to do distribution here. So we have 2a squared plus 16a plus 32. And now this is a minus a plus 4 in parentheses. So I'm going to do a similar thing and distribute the minus a minus 4 plus 3. Okay, I think I can simplify this one more step. 2a squared, and then I have a plus 16 and a minus a, so that's a plus 15a. And I have a plus 32 minus 4. Okay, that's 28. Plus 3 is 31. And that is that f of a plus 4 fully simplified. Took a few steps, but after the first plug-in step, it was just some rearranging and simplifying. It's that plug-in step that typically is the hard part. So when we want to graph a function, we do the same thing as when we graph equations. We think about them in terms of ordered pairs, but instead of just x, y, we can think of x, f of x. And we plot the points and draw the graph the same way we always do. This time we're going to remember f of x is the output of what happens to x. And we're going to note that y is also the output of x. And so yes, they are basically two ways of writing the same thing, and you'll have to get used to working with both. So you might see things like f of x equals x squared plus 1, and you might see y equals x squared plus 1. Typically, you're not going to see a huge difference in the two. We just know that this x in here gives us a place kind of as a thing we can plug into. But overall, they're pretty interchangeable. Okay, so same as before, whenever we have something like x squared plus 5, right in here, there we go, right in here, we will take our inputs x, figure out the outputs f of x, and we plot them on our graph. Now, this is no different than how we did x and y, right? But we're just calling it f of x this time. And so the same idea here is we have the graph of x cubed minus x, and you'll notice that this is the same idea as if we had y equals x cubed minus x, right? Still the same idea as plotting lines. And similarly, we can have the square root of x plus 4. And same idea, we're just using f of x. We very well could have written it x plus 4 like this. Either way works. These are just some of the examples of functions that you'll have to get used to working with. Okay, so now we're going to actually use the graph to figure out the following function values. So for part A, it's f of negative 3. And so negative 3 is going to be our x value, right? It's sitting in place of where the x goes. Okay, so I want to know what is f of negative 3, or basically what is my y value at negative 3. We'll say x equals negative 3. Well, I'm going to go to my x value, negative 3, and I'm going to see where is my graph hitting. Well, it's hitting right here. When I go to negative 3 and I go up to the graph, I'm here. Well, what is my y value there but 3? Which means my y value, or my f of x value, f of negative 3, is 3. Okay. Similarly, f of 1. So that means we're going to think about, okay, what's happening? What is my y value when x equals 1? So I'm going to go to x equals 1 on the graph, and I'm going to go down to where it's actually touching my function. And I look at my y value, and I get y equals -5 right there, which means f of 1 is -5. Another clear example of how the y and the f of x are really the same thing. Now, it's actually really easy to tell if a graph is a function by using this thing we call the vertical line test. And what we do is we take our pencil, and you're going to hold it horizontally along as essentially parallel to the y-axis, so up and down. And we're going to see if the graph crosses your pencil in more than one place. So to look at an example of this, imagine I'm holding my pencil up and down like this, and I'm going to move it along the graph like that. And if it doesn't touch this graph in here, if it doesn't touch my pencil more than once as I'm moving along, that means it's a function. So in this guy, as soon as my pencil hits right here on this line, I'm actually touching it in 3 places. That means it's not a function. This one is a function, right? Okay, again over here, when I cross my pencil right through here at a vertical line, it hits in 2 places. So this is not a function. All right, just a few more examples here. The the graphs here, which one of these are functions? Well, clearly this one is not. It touches at 2 places right here as I again hold my pencil along. This guy is kind of crazy looking, part E, but it is technically a function. There is nowhere where if I hold my pencil up like this, there's nowhere where it would actually touch in more than one place. So that one's good. Okay, now this last one is even crazier because it's actually broken into 2 pieces. But notice how this dot is open and this one is closed. That means that the value at -1 goes with the closed dot and not the open dot. And so this only has one value at each of my vertical lines, and so it is in fact a function. So the next thing that we want to talk about in this class is to formalize the idea of a domain. We've been using it a whole bunch kind of as we talk about the inputs, but really this is a definition you guys should know. So anytime we think about a domain, it's a set of all inputs for which an output exists. So when an input results in an expression that is not a real number, we say that that value does not exist. And so that number cannot be in the domain. So a really quick example to bring this home is something like if my function is f of x equals 1 over x, then 0 cannot be in the domain since 1 over 0 does not exist. And so whenever we want to think about finding the domain of a function, we can either think about if it divides by 0. There we go. My pen disappeared for me. If it ends up in dividing by 0, or if we end up trying to take a square root of a negative value. And so if neither of these two are an issue, we actually just write that the domain is the set of all real numbers from -infinity to +infinity. So we write the domain down as an interval of values on the number line. So we have multiple different ways of representing an interval. We will, if not already, have talked about this on the worksheet for the corresponding lecture. And it's frustrating because intervals can look a lot like ordered pairs, but we just have to keep the context in mind of what are we talking about right now. So we either use parentheses and brackets. So for example, if we have 0 to infinity, the 0 is included because we're using a bracket, and infinity is never included. Similarly, we can use inequalities. So instead we could have used this x, we read this also as x such that x is greater than or equal to 0. And this also means all numbers from 0 to infinity with 0 included. So either one is okay. Either the homework will specify what you're supposed to do, or you guys can just pick one. But anytime we need to join two intervals, we use what's called a union. So if I'm trying to write down all numbers except for x equals 3, I write it down negative infinity to 3, union 3 to infinity. 3, of course, is not included here. So given that given this function, f of x is 1 over x minus 3, find the function values that were given and determine whether the values are in the domain of the function. So we're going to start by figuring out f of 1, and that is exactly going to be 1 over 1 minus 3. And we can simplify that a little bit by doing 1 over 1 minus 3 is negative 2. Negative 1 half is the result. That value certainly does exist, and it is certainly in the domain. 1 is in the domain, is what we say. And now we're going to think about f of 3. So we're going to plug in 3 for x and think about f of 3. I won't rewrite it. F of 3 equals 1 over 3 minus 3. Well, that's 1 over 0, which does not exist, which means 3 is not in domain. So what is the domain of this function? Well, really, we want to think about any time where my bottom denominator here is 0. So the only time x minus 3 is 0 is if x equals 3, like we saw in the last problem. And so we write the domain down as the interval from negative infinity to 3, union 3 to infinity. Now let's move on to the next example. So find the domain of this function. Again, it's a fractional function, so we need to look at when our denominator is 0. That's the only time this might not be defined, is if an x value leads to that being 0. And so we're going to set that equal to 0 to find out when that happens. In order to do that, we need to factor this guy. And we need to think about values that multiply to 3 and add to positive 2. And so I'm going to put a plus 3 and a minus 1 because I know negative 1 times 3 is negative 3. And I know negative 1 plus 3 is positive 2. Okay, so I set this equal to 0. Then I'm going to set each term equal to 0 to find my zeros. Plus 3 equals 0. Okay, I add 1 to both sides and I get x equals 1 over here. If I subtract 3 from both sides, I get x equals negative 3 over here. Which means those are the two x values that are not in the domain. So to write down my domain, I'll write it as negative infinity to negative 3, union, essentially we're skipping over negative 3, to 1, union 1 to infinity. So anytime I'm trying to skip a particular number, I use parentheses and we just skip over that number, and it looks just like that. So we talked about domain a whole bunch, and range, domain being our set of inputs, well, the range, of course, is our set of outputs. And they're always found along the vertical axis, okay? So essentially, the domain is, well, what are all the x values going in for this function? And the range are, what are all the y values going in for this function? So what I mean by that is we look at the graph, and we say the domain is everything that we have an x value for. So see, once I get down to x equals negative 5, there's no function over here, which means my domain starts at negative 4, and it goes on, well, the arrow means it goes on forever. We always use parentheses with the infinity. And because we have a closed dot down here, we know to use square brackets for the negative 4. And that's my domain. That's everything that has something on the function. Everything along my x-axis has something on the function. Now my range is similarly all of the y values that are touched by the function. So along here, clearly there are no negative values. There's nothing down here like this, right? So there's no negative values in my range. But I see a whole bunch of positive values. I see something at 0, I see something at 1, I see something at 2, and we can just keep going. And so if I want to write down the range, I want to go from 0 to infinity. So those are all my y values along here that have some x value. And 0 is included because it's a closed circle. So that's what my range looks like. So again, just count all the values along the x or y axis that the function actually touches. Okay, as in somewhere along here, it touches one of these y values. And now, the last thing I want to share with you is how we sometimes look at functions for applications. So a lot of these kinds of questions will give you more information than you actually need. And I want you guys to just really focus in on what is the actual function and where am I evaluating the function at. All right. So this one is boiling point and elevation. If the elevation E is measured in meters above sea level, at which the boiling point of water is T degrees Celsius, is given by this function. E of t is 1,000 times 100 minus t plus 580 times 100 minus t squared. And all I'm going to do, well, it asks for, at what elevation is the boiling point 99.5 degrees and 100 degrees? And the elevation then is given by E, right? And the temperature is T, which means these temperatures I'm given should probably go in place of T, which means we need to find E of 99.5 and E of 100. Well, if I plug in 99.5, I get 100 minus 99.5 plus 580 times 100 minus 99.5 squared. That first one is going to be some kind of decimal, so I'm going to leave it to you to plug in your calculator and see what we get. But we can go ahead and do the other one. That looks like 1,000 times 100 minus 100 plus 580 times 100 minus 100 squared. Oh, well, 100 minus 100, that's easy to do in our heads. That is just 0. So we get 0 for the second one, which makes sense. At 0 meters above sea level, the boiling point of water is 100 degrees Celsius. Hopefully you remember that from science class. If you don't, not a big deal. But yeah, that is how we actually use functions in real world problems, right? A lot of times it just comes down to plug in the value that you're given.